Thank you. I have a cold, so my voice isn't quite here. So towards the end, I might just be waving to you. So we'll see. A short aside, you might wonder, why did I have the music of a 1970s soap opera as my music? It was the theme to Dallas. I went on a cruise to Antarctica, and whenever the captain came to the stage, they played this music. So I thought, yeah, that is ridiculous. I'll pick that. Okay. So what is Verse? It's a new programming language that is really the brainchild of Tim Sweeney, who is the founder of Epic Games. And an early version of this is already part of sort of Unreal Engine. So it's called UEFN, Unreal Engine for Fortnite. But there are much more stuff coming that will come in later releases. So it's a functional logic language, so it's very niche, I would say. It has effects, it's statically typed. There's lots of stuff in Verse. I'm only going to give you a short overview of the things that are a little bit different from regular functional programming. So what's Epic Games, and why is Epic Games doing a programming language? Well, it's a computer games company, and Tim Sweeney started it in 1991, and he owns the majority of it still. We're about 4,000 people, and there have been various games over the years, but in 2018, Epic released Fortnite. I don't know, do we have any Fortnite players in the room? No. Oh, okay. Thank you. Thank you for helping me with my salary. So the Unreal Engine is the game engine behind that, and that is really used for a lot more things than games. So movie and TV productions, if you've heard of virtual production. Also, it's used for user interfaces in cars. I'm not quite sure why, but General Motors is using it. So if you want to program Unreal Engine today, there are two choices. There's either a sort of graphic programming language with boxes and arrows, and you connect things together, which is very good for simple things. Or there is C++, which is not good for anything. I mean, performance, yes. But for people who make games, they're interested in making games. So the idea with Verse is that it's going to be a safe language that is easier to use. You can't make mistakes as easily. Do we need a new programming language for this? What is this? Well, Tim Sweeney is really a programming language nerd. So it's interesting to have a CEO that is really into programming languages, and he thinks we need a new language for this. And he's been tinkering with this for the last 20 years. So there's a bunch of people who've been working on this. And so what are we doing? We're trying to figure out what Verse really is, what's in Tim's head. I'll show you pictures in a moment. So we have one paper at the ICFP conference about the reduction semantics. We're doing a denotational semantics now. And there's this called the thing called the verifier, which is really like a type checker that we're working on as well. So this is Tim, and he's been thinking about this for a long time. And here's us, and we're trying to suck out the meaning of Verse from Tim's brain. We have a 2-hour meeting with him every week, and we suck, and it ends up like this every time. There's a lot of stuff coming out of Tim's brain. So I'm going to show you some examples. That's how I'm going to present most of Verse. So here is a factorial function, and it looks kind of familiar, but some of the things here, they are not what they seem to be. They do what you think it should be doing, but it doesn't do it in quite the way you think, probably. I'll get back to what that actually means. Here's another example. let's only look at the first one. So it's the fib function. And again, I'll come back to why this is not quite what you think it is, but it does what you think it does. So an interesting thing here is you can have an argument saying, well, on the third clause there, n is a natural number and n is greater than 1. So that's sort of a cool thing you can say in verse. You can have types more refined than just saying that it's a nat. Okay, so you're going to see a lot of snippets of verse code. And so when you see colon equals, that means we're defining something. So that there will be a variable to the left and some expression to the right. And these definitions, they can occur anywhere. They don't have to be sort of on separate outside of expressions. They can occur in the middle of it. So we can say that, oh, x is equal to 3 and I want to add x to it. So that x will scope over a block, whatever that is. So you can see some examples here at the bottom where, can you see the red x? I don't know. Yeah. So that x is out of scope. So you can say x colon equals 3, that is only visible inside this block. Or if you have an if and you set something in the then branch, then that's not visible anywhere else, because you might have ended up in the else branch and then x would be a meaningless thing. So that's a little bit unusual. Here's another unusual thing. If you compare things, there are no booleans. Instead, there is a notion of failure. Failure is not something bad in verse. That can happen to expressions. An expression either succeeds and gives you a value, or it fails. And that's a normal thing. It's a bit like being in the maybe monad in Haskell, or the option type in many other languages. You're sort of in that context whenever you're allowed to fail. So if you compare two things like 3 is less than 4, well, it is, and then it will return the first operand for less than, so that returns 3. 4 less than 3, that's not true, so that will fail. So a cute thing about this is that you can write the thing that is at the bottom here, 0 less than or equal to I less than 10, and that actually works. So these comparison operators are right associative. So it will do this thing first, I less than 10, so that might fail, and then everything fails. If it succeeds, it returns I, and then you compare that to 0. Now it fails, then everything fails, and if it succeeds, you return 0. So this is not really sort of the big meaning of having these kind of failure things, but it's a cute thing you can do. And to handle failure, the normal thing you do with it is to have an if. So sort of at the top level of your program, you're not allowed to fail. The whole program is not allowed to fail. You can only fail in a context that can handle the failure in some way. And the main thing to do that is an if. So if the condition fails, you get the else branch. If the condition succeeds, you get the then branch. Nothing really strange. Some kind of nice thing you can do is something like this. X is foo of 3, and whatever you bind in the condition is available in the then branch. It's of course not available in the else branch, because if you fail here, there is no binding for X. So that's kind of a nice thing to be able to do, that you can compute something in your condition and then use it if it succeeds. Oh, by the way, if you have any questions, you can interrupt me if you want to, or you can save it to the end. I will try to stop now and then and see if there are any questions. Are there any questions? Yes.
The previous slide, why do you do it that way? Why?
Why do it which way?
Returning first.
Well, you have to return some value. So why do you return the first? It's a choice. You could have decided to return the second value, or you could have decided to always return 42, but that seems less useful. I mean, one of the two operands might be useful to do more stuff. And so it returns the first, and then making it right associative makes this work. So here is the first little weird thing. Well, not. The other ones might have been weird too. There's more weirdness here. There are two ways that you can make function calls, with square brackets or with round ones. If you do square brackets, you're saying, okay, I'm aware that this function call might fail. And it's okay. You have better handle it in an if. So if you saw this one, I had square brackets here saying, okay, I know that calling foo with 3, it might fail. If I use round parentheses, that means this call is not allowed to fail, and the verifier/type checker will, at compile time, make sure that it doesn't fail. So if it can't verify this, then you're out of luck. You'll get an error message. I mean, hopefully it will be able to deduce this most of the time, but not always. Functions are marked if they can fail or not, so it's sort of not as difficult as you might think. So this is a functional logic language, which means we have logical variables and unification. What does that mean? Well, it means you can introduce variables that don't really have a value. So x:int says, yeah, x is an int. I don't know what value it has yet. And then you can, at some other point, bind it by unification. Unification is written with an equal sign. So this first thing says, well, x is an int, and oh, yes, it's 5. If you try to do something like saying x is 6, and then you say x equals 5, well, 5 and 6 are not the same, so this line would fail. It's a failing computation. And if you try to set it to x to 5 once again, 5 is equal to 5, so that's fine. And since it's unification, it means you can unify things that are not necessarily just variables. So here we have some pairs. So x and y are ints, and we're saying that x, the pair x comma 2 is equal to the pair 1 comma y. And if you do that unification, well, x must be 1 and y must be 2. So multiple things can happen in these unifications. So it's a very powerful thing to have unification. You'll soon see how it's nice when you make function definitions. It does make things more complicated in the semantics. Yeah, and you can have all kinds of expressions that sort of that you can unify. So and the order of these things doesn't matter. So all these things do the same thing. I mean, it doesn't have to be an x to the left of the equal. It can be on the right. You can have the declaration to the left of the equal, and so on. Here's another peculiarity of the language. You can have these choicey expressions. So 1, choice 2. That expression has, first it has the value 1, then it has the value 2. What does that even mean? Well, I mean, you can think of it over time that you're sort of repeating the computation that this is in. But if you look at the next line, x equals 1, choice 2, and then x plus x, x is not bound to something that is a choice. X is first bound to 1, and then we compute 1 plus 1, and then x is 2, and we compute 2 plus 2, so it yields 2, 4, and not some weird combination of 1 and 3 and 4. So a variable always stands for a single value, but you might repeat your computation multiple times with different values. Yeah, if you do 1 choice 2 plus 1 choice 2, you get 2, 3, 3, 4. Choices are sort of iterated from the left to the right. A little more example in a moment. There is a for loop construct that takes choices and turns them into tuples or arrays. Tuples and arrays are the same thing, inverse, so you can think of them as either. So this says, I have a choice between 1 and 2 and 3, and for all of these, we return 12. So you'll get an array with 3 elements that has 12 for all of them. Or you can say, well, x is equal to 1 or 2 or 3, and I will return x plus 10. And then you'll get 11, 12, 13. You can do have multiple of these choices. And as I said, they go from the left to the right. So if you have x is 3 or 4 and y is 6 or 7, you'll get 3, 6, 3, 7, 4, 6, 4, 7. So not so strange. The second one is a bit strange. So the first one you could write in, say, Haskell or Python as a list comprehension with 2 generators. The second one is weirder because I say x is equal to y or 4, and then y is equal to 6 or 7. So this works inverse. And what you get, well, first x is y, so it's 6, and then x comma y, that will be 6, 6, and then y will be 7. So then x will be 7 as well, so you get 7, 7. And then x will be 4, y will be 6, and then y will be 7. So a bit strange that you can use sort of the values, the variables of y there before you've sort of introduced it, but it works. Questions? Yes. Is the semantics what? You might be able to do it with monad fix. I have not tried. Yeah, perhaps. Probably. So that this for loop turns choices into arrays. You can also turn arrays into choices. It's written colon. I will explain in a moment exactly what colon does. But if A is the array 2, 1, 5, and if you write colon A, that's the same as 2 choice 1 choice 5. So roughly you can say that 4 and colon are each other's opposites. So if you have turn an array into choices and then you turn it back into an array, you get the same thing again, and the other way around it. You have a bunch of choices, turn it into an array and go the other way. So is verse a strict or lazy language? The answer is no. It's neither. It's what we call lenient evaluation, which means it's a bit like strict evaluation. So everything will be evaluated the way it would have been in strict if you had a strict language. But the order in which things happen is not as determined as it is for strict evaluation. So things can happen a bit out of order. So if you look at the second example, you say that y is x plus x, and then later on you learn that x is 3. That's fine. If you have effects do happen in the order that the program specifies. So the effects happen in order, but the actual computation of values might happen out of order. So if I print x and then I print 5, and then I learn that x is 3, this will print 3 and then print 5, because the printing will sort of stop here. It will not print anything because it doesn't know what x is. And then, oh yes, x is 3, then it can print 3, and then it can print 5. It also means that some of these little tricks that you can play in a lazy language, you can also play here. So here, this function, it returns 1, x. And if you say, okay, I'm going to call f, and the input to f will be a, and the thing that returned here, you destructure that pair into a, b. So in a strict language, this wouldn't work because you couldn't compute a here, because you don't know that yet. It comes from this pattern matching. But in a lazy language, it would work, and in the lenient version of it, it works too, because you call f, you don't need to have a yet, and then that will return 1, and whatever you passed in, and then you know, oh, a is 1, and then b will also be 1. Any other questions? Okay. Or just to have a even more peculiar example. So we start by printing the length of the array A, and then we compute the array A with a for loop that prints the elements. This will work, strangely. You can't print the length because you don't know the length yet, so you have to execute the loop. But in the loop, you can't do the prints, so you sort of save up the prints for doing. The reason you can't do the prints in the loop is that you haven't done the print of the length. I mean, the effects have to happen in order. But it's okay, you can still run the loop and just say, okay, I'm saving up these prints for later. And then you learn that, oh yeah, the length of the array is 3. Because there were 3 iterations here. So then you can print the length, and then all the other prints happen as well. I'm not sure why you would do this, but it's just to show you that leniency can do, let's call them interesting things. Oh, it says weird there. You can do weird things. So now I'm going to say a little bit about types and functions, because they're some of the most interesting bits. So there are static type checking in verse, but types are, there are sort of, a type can contain any collection of values. It's not like we only have integers or characters or something like that. You can make your own types that contain whatever you like. Because in verse, a type is a first-class thing. A type is just a function. Or it's a function that returns its argument if it's in the type and fails if it's outside the type. So int is a primitive type. And if you say int, you call the int function, because the type is just a function, with 5, it will return 5 because 5 is an int. If you call it with something that's not an int, it will fail. So it's a bit like having contracts or something like that. They are types are executable, and you can make new ones. I'm not going to talk about that. Here, I'm making some new types. I'm coming back in a moment to what the closed thing means. So I'm saying, I'm defining a function 0. The function 0 takes 0 as an argument and returns 0. So that's a function that when given 0, it will return 0. When given anything else, it will fail. So that can be used as a type. That's a type that only contains 0. Here's a type that contains 1 or 2. So I say 1 or 2 is a function. its argument is 1, choice 2, and I return x. So for 1 or 2, it returns its argument, otherwise it fails. So that's the type that contains 1 or 2, and here's a function that contains natural numbers less than 5, and I use one of these where clauses that sort of limits what x can be. Since you can make your types be anything, I mean, you can have arbitrary expressions there. Of course, type checking is undecidable because you can't decide statically at compile time if something is in a type or not. So this verifier, it will do its best, but it will sometimes say, I can't tell you if this is type correct or not. It might be, it might not be. It can tell you this is definitely wrong, or it can tell you that it's right, but sometimes it won't be able to tell. Okay, a little bit about functions. So I had a closed there. When I say closed, it means that this function fails outside of its domain. So if I say f of 0 closed is equal to 1, that means if I give it 0, it will succeed. If I give it anything that's not 0, it will fail. And so if I, for instance, do f of round parentheses here, that would be a compile time error because I'm calling it with something that is not in the domain of the function. The domain is only 0. If I have an open function, which is the default if you don't say anything, then the function says, well, I know what I am for 0, so g of 0 is 1. But if it's not 0, g has no opinion. It could be anything. So calling an open function outside the domain is also a compile time error. It doesn't fail outside. It's just you don't know. So the verifier will make sure you don't call open functions outside the domain. So what's the point of open functions? Well, that's how overloading works in verse. So if I could define some function toString for an integer that returns a string and it's equal to something, and the same for float. So the first clause says, well, I know if it's an int, then it will return a string. And the second one says if it's a float, it will return a string. So there's only like one toString function, but it can handle both ints and floats. So overloading is handled by having these open functions that say, I know how to handle part of the domain, and I know how to handle another part of the domain. So this handles int, and it handles float. So what about this? Well, this is really overloading in effect. The first clause says, well, I'm a function, I know I map 0 to 1, and the other one says, I map 1 to 1, and they're both open. So you can sort of combine them and say, yeah, together they make a function that maps 0 to 1 and 1 to 1. And then I can't read the red stuff there. So open functions, if you have multiple open functions that you combine in this way, you're not allowed to have overlapping domains. Because if you had overlapping domains, the compiler wouldn't be able at compile time to decide which one you're going to use, or at runtime for that matter. So if you want to have, here's a slightly more readable. So if you just wrote fib and said, here's the sort of the recursive case, and it takes a natural number, that thing would be rejected by the compiler because that contains 0 and 1. And I've already said how to behave on 0 and 1. So I can't say, give something other definition here. So you have to say, well, if n is if n is greater than 1, then we can do this recursive case. And if you can see here, I've used round parentheses here, so there's some work here for the verifier. It has to make sure that n-1 and n-2, that those calls can't fail. And it can verify that. If n is greater than 1, then this will be 0 or greater, and that will be 0 or greater, which means it falls into the domain 0, 1, and the rest of the natural numbers. And you could, of course, add more overloadings to fib if you want to. That would be okay, but weird. So when I write the function definitions like that, f of some that looks like a pattern, that's really short for this function. So that function is how you spell lambda in verse. So it's lambda p e. And what are they? Well, p is just an ordinary expression. It can be any expression. There's no separate pattern language in verse. Patterns are the same as expressions. And that works because of the unification stuff. I'll show you here in a second. So here I have a function application. So function, there's a lambda here, so lambda pe, and I'm applying it to the argument a. So what happens roughly is that p, the sort of the pattern for the argument, is unified. Think of it as unification for now. It's not quite unification. I'll explain in a moment. P is unified with a, and then we compute e in this environment that we got from that. So function x int x plus 1, and we apply it to 5. So we take the argument thing, x int, we unify it with 5, and then we compute x plus 1. Well, if we unify x int with 5, that means x will be 5, so x plus 1 will be 6. Like Haskell, all functions have a single argument in verse. And the thing that looks like multiple arguments are just tuples of arguments. So if you have an xy tuple here, the same thing happens. If you call it with 3, 4, you will do this unification, which will make x equals to 3 and y equals 4. So I think this is quite elegant. You don't have to have a separate pattern language. It's the same. And because expressions can have these variable bindings in them, it sort of works out. But you can do more than this. So here I have a function f maps 0 to 1, and x is an int, and then I call f with x. What happens now? Well, x is an int, and then we unify x and 0, and we compute 1, which is useless. We throw that away. And then the result of the whole thing is x. Well, here the data flows the other way. X becomes 0 because the only choice here with f is that the argument is 0. So that's what x will become. So you can get values. The function can sort of set values that are arguments to it. Yes, another little interesting thing is if you don't have a colon when you sort of define a function, then you're not binding anything. So if I say, like here, f2 of x equals 1, there's no colon there. That means that x is a value, and it happens to be 0, which means that the pattern is like a 0, which means you can sort of name patterns in verse without any special machinery. You can just give them a value like that and use them as a pattern. I have another 5 minutes or something. Yeah. So here's another little interesting one. So now the function says the argument can be 0 or 1. There's a choice. Okay, and I'm going to call the function f with some variable I that doesn't have a value yet. So if we follow the recipe, what I said is that, well, I is an int, and then we do this unification. 0 or 1 is equal to I. And we have a 2 that we're not going to use. The curly things are a block, and then we return I. So that means that I will be 0 or 1, and the whole result of this is the same as 0 and 1. So this function can actually enumerate its domain, and we can figure out what values are acceptable to f. So that works for these kind of functions that do choices in the domain. Here's a variation where there is no choice. This would just get stuck because there's no order in which we can enumerate. So x can only be 0 or 1 here too. X is a natural number less than 2. But this will be flagged by the compiler saying, I don't know what this is. There are multiple solutions for this equation, and there's no order. So inverse arrays are just functions. So if you see this array 1, 5, 2, it's the same as this function that says the argument can be 0, 1, or 2. Arrays are just indexed from 0 and up. If I is 0, you get 1. If I is 1, you get 5. Otherwise, you get 2. So arrays are not sort of a different concept. You can encode arrays by just using functions. So an implementation would not do that. I mean, you want your arrays to be something more clever than functions. You want constant access time. And you can iterate over the elements of an array with a for loop like this thing here. So this, I haven't explained exactly what that means, but that works. The x:r works for both arrays and functions if the functions can iterate. So what does x:t mean? So it's a shorthand for saying x is equal to :t. And then I have to explain what :t is. :t is a shorthand for this thing. So now I'm saying exists I. What do I mean by that? I just mean a new variable. I don't know anything about the value of this variable. And as I showed you before, if I call a function with some unbound variable, that means that the function can set this variable to different things. So if this is an array that can enumerate its domain, it will set I to 0, 1, 2, and so on. And then you call the function with 0, 1, 2, and it will return whatever the function returns. And so :t, if you write :t, and the thing can enumerate its argument, whether it's an array or a function, you will get the values of the array or function. So if you, in this thing, do :r, that means you will get 1, 5, 1 choice, 5 choice 2, which is peculiar. So this :t sort of, it makes double duties. It both says something is of a type, and it also says you can enumerate the arguments. So what does it really mean when I have been saying x:int? Now we get to sort of reveal the truth about what x:int means. Well, if we expand it, as I said, x:t means x: equals :t. So it means x: equals :int, and :int. :int is really shorthand for the t with an existential. So it means this. So what is this? Well, it's some kind of equation that has two unknowns, I and x. Is there a way to solve this? Yes. If I is 5, then int of 5 is 5, which means x is 5, and we have a solution. So the thing you thought you knew what it meant, x:int, it doesn't quite mean that, but it turns out to mean the same thing in the end. It means, is there some argument you can give to int so that you get, there must be some argument you can give to int so that you get the x. And x is supposed to be 5 here, so that works. Yeah, so I'm not going to tell you about what almost unification is. I can leave you with a slide to ponder. Okay, questions? Yeah. So a simplified version of this is part of the Unreal Engine for Fortnite. So there are thousands of people out there making a living programming in verse. Well, I mean, actually, they're making a living on making games. So since there are very few Fortnite players here, I'll say a little bit how it works. So Fortnite is a game that mostly is Epic's game. You have an island where things happen, but you can add new islands. Anyone can add a new island. And there are lots of tools to make your island pretty. I mean, there are lots of assets, trees and buildings and things like that, and guns and what have you. But if you want to give any behavior to the things you have on your island, that has to be programmed in verse. So there are people who make more islands, and then they sort of do a little verse to hook things together. And then they have a sort of an extension. And when you enter Fortnite, you can say, I want to play the main game, or I want to jump to one of these islands. And then Epic does revenue sharing with all these people. So depending on how many people play the different islands, we do it sort of fairly across the board. So if someone island suddenly becomes more popular than Epic's own Fortnite, then they will get more money than we do from the money that people pay to play Fortnite. Actually, playing Fortnite is free. It's getting all the clothes and the makeup and things that cost money.